In this session, we will discuss about vapor pressure, partial vapor pressure, Dalton's law of partial pressure, and Raoults law. First, we will discuss about vapor pressure. The pressure formed by the vapors of the liquid over the surface of the liquid is known as its vapor pressure. Here we can see that when the water evaporates, the molecules escape to the gaseous phase and there they exert a pressure on the surface of the liquid as well as the walls of the container. We will now make a comparison between vapor pressure of water as well as the vapor pressure of alcohol. Alcohol vaporizes at a faster rate compared to that of water. So, the vapor pressure created by alcohol will be significantly higher than what is created by water. This is because water has got strong hydrogen bonding. Now consider a mixture of gases. The pressure exerted by an individual gas in a mixture of gases is known as its partial pressure. Here, gas A, B and C combine together to form a mixture of gases. The pressure exerted by each gas is known as its partial pressure. The total pressure is the sum total of partial pressures of A, B and C. Raoults law established the relationship between mole fraction of a component and the partial pressure exerted by it. According to this law, the partial vapor pressure of each component in a solution is directly proportional to the mole fraction of it in the solution. Now, if P1 and P2 are the partial pressures exerted by the component 1 and 2 at a certain temperature, then according to Raoults law, P1 is proportional to X1 or P1 equal to P1 naught X1, where P1 naught is the vapor pressure of the pure component 1 at the specific temperature. Similarly, P2 equal to P2 naught X2, where P2 naught is the vapor pressure of the pure component 2. Now we will study about Dalton's law of partial pressure. According to Dalton's law of partial pressure, the total vapor pressure of a mixture is the sum of the individual vapor pressures of the components of the mixture. P total is equal to P1 plus P2. Or we can define P total is equal to X1 P1 naught plus X2 P2 naught. Let this be equation number 1. In the part 1 video, we have learned that the sum of the mole fractions will be equal to 1, that is X1 plus X2 equal to 1. Rearranging this, we can get X1 is equal to 1 minus X2. Now we will substitute the value of X1 in equation 1. Now we will get P total is equal to 1 minus X2 into P10 plus X2 P20. Let this be equation number 2. Now we can see that the P total is a linear function of mole fraction X2 as P1 naught and P2 naught are constants at a specific temperature. Now, if we plot a graph of partial vapor pressure of the first component versus mole fraction corresponding to the equation P1 equal to X1 P1 naught, a plot as shown here is obtained. In the graph we can see that when the mole fraction of the first component becomes 1, the partial pressure of the first component is equal to the vapor pressure of the pure component 1. Now, a plot for component 2 based on the equation P2 equal to X2 P2 naught on the same set of axes is as shown here. From this graph, it is evident that the vapor pressure of the pure component 2 is higher than that of the vapor pressure of pure component 1. This means that the component 2 is more volatile than component 1. Now, according to Dalton's law, the total pressure of the binary mixture P total is the sum of individual partial pressures, that is P1 and P2. Here the solid red line indicate the plot of P total versus mole fraction. Based on Raoults law, liquid solutions can be classified into two: ideal solutions and non-ideal solutions. First we will discuss about ideal solutions. A solution that obeys Raoults law over the entire range of concentration is said to be an ideal solution. For an ideal solution, the enthalpy of mixing as well as the volume of mixing of the pure components is zero. This means that no heat is absorbed or evolved, and also there is no change in volume on mixing the two components. For example, if 50 ml of hexane is mixed with 50 ml of heptane, the volume of the resultant solution will be exactly 100 ml. Also, no heat is absorbed or evolved during the mixing of the two components. The ideal behavior can be explained on the basis of intermolecular attractive interactions between the two components. If A and B are two components, then in an ideal solution, the magnitude of A-B interaction will be same as that of AA and BB interaction. But in real life, there is no such thing called an ideal mixture. But some liquid mixtures come fairly close to that of the ideal mixtures. These are mixtures of components that have almost same properties. Some common examples of mixtures that shows nearly ideal behavior are hexane and heptane, benzene and methylbenzene, chloroethane and bromoethane. Since ideal solutions obey Raoults law, they show a graphical representation as shown here. Let us now discuss about non-ideal solutions. The solutions that do not obey Raoults law over the entire range of concentrations are said to be non-ideal solutions. The graphical representations of non-ideal solutions will produce curves rather than straight lines in the case of ideal solutions. The dotted straight lines represent the ideal behavior, whereas the curves represent the deviation from the ideal behavior. The reason for the deviation are interactive interactions between the components of the mixture at the molecular level. For a non-ideal solution, the magnitude of AB interactions are different from that of AA and BB interactions. Also, for non-ideal solutions, the enthalpy of mixing as well as the volume of mixing will not be equal to zero. If the magnitude of AB interactions are less than that of AA and BB interactions, then there is a greater tendency for the molecules to escape to the gaseous phase and thereby show higher vapor pressure. Such solutions are said to exhibit positive deviation from Raoults law. The total vapor pressure of such a solution will be greater than that of the vapor pressure corresponding to that of ideal solutions with the same composition. For example, the mixture of ethanol and cyclohexane shows positive deviation from Raoults law. Before the process of mixing, the ethanol molecules are in close association with each other due to extensive hydrogen bonding. When cyclohexane is added to ethanol, the cyclohexane molecules get in between the ethanol molecules and there is a significant decrease in the hydrogen bonding between ethanol and ethanol molecules. Now it becomes easy for the ethanol molecules to escape to the gaseous phase and show a higher vapor pressure and thus exhibit positive deviation from Raoults law. For solutions exhibiting positive deviation, the enthalpy of mixing as well as the volume of mixing will be greater than 0. Methanol and water as well as carbon tetrachloride and chloroform are some of the examples that show positive deviation from Raoults law. We will now discuss about negative deviation from Raoults law. For such solutions, the magnitude of AB interactions will be greater than that of AA and BB interactions. For such solutions, the components will be held together by strong molecular interactions such as hydrogen bonding, and thereby their escaping tendency decreases, and hence they show a lower vapor pressure. This in turn results in the lowering of the total vapor pressure. This type of solutions are said to exhibit negative deviations from Raoults law. For example, when acetone and chloroform are mixed together, a strong hydrogen bond is formed between the two molecules. Now, these molecules can no longer escape to the gaseous phase, thereby their vapor pressure decreases. Also, the total vapor pressure of the solution will also decrease. For the solutions exhibiting negative deviations from the Raoults law, the enthalpy of mixing as well as the volume of mixing will be negative. The pair of solutions exhibiting negative deviation from Raoults law are first, phenol and aniline, second, chloroform and diethyl ether.